Okay, so I think we can start now. So welcome to the live session for week 8 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur, and I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting in solving some of the similar assignment problems that have been given to you in the week 8 assignment, so that it will help you in solving the assignments easily, and it will develop some of the remaining concepts that you might lack from the video lectures. So we have almost covered like most of the physics and the physics part of each of the devices. And in the last week we started with some of the modeling. So the first uh, thing that we went into was the semi-classical transport theory, in which we dived into this distribution function, that is a Fermi-Dirac distribution function. We see some of the Boltzmann transport equations, that is the BT equations, and yeah, RTI skipped because it was quite, I mean, straight away you can see the derivations and all in the video lectures. And then I covered some of the concepts of scattering and mobility, and we did a lot of numericals regarding the same. So as you can see, we have already covered the device part in the first 6 lectures. We have covered the PN junction initially, then the BJT, then we went towards the main device, that is a MOSFET. Uh, yeah, So once covering the device part, what we did was we started with the modeling aspect. So as you can see in the week 8 and 9 lecture, they are both on dependent upon the DD models, that is the drift diffusion models. So we'll be covering some of the drift diffusion models, I mean some of the part of that, and we'll also see some of the derivations, because there are many different phenomena and many different cases we can take, such as there are generation and recombination model. They can be also in some different phenomena, such as it can be in steady state, it can be let's say it does not have any generation and recombination, etc. So there are many different types of phenomena that can happen, so we'll also look into that. So week 8 and 9 will be like half and half lecture for the drift and diffusion models, as a syllabus suggests. So to start with this, as the name suggests, we have drift diffusion. So we kind of looked into the drift equation, I mean more pronouncedly, because what we were doing is we were doing the derivation for drift velocity, which came out to be mu e, and we came up to the part that the current density due to the drift was nothing but the drift current density due to the electrons, and the second is uh, give me a moment. Okay, so let me share in just 1 minute. Yeah. So we covered the drift part, as I was saying, that we have some holes and we have some electrons. So we came to know that the drift region was nothing but NQ mu n. So the whole term will be multiplied by the electric field, and it is due to the holes will be PQ mu P, and whole times the E. So this is nothing but the conductivity sigma. And this is the, I mean, in general formula that we were following to calculate the current density or whatever we have in, let's say, in terms of conductivity. So the conductivity will always remain same in terms of drift, but what we did not focus on was the diffusion part. So in general what we have is the total current density is both having the drift component, and also it does have the diffusion component. So we have already talked about the drift component in detail, that this is a drift component. And sorry, Yes, so as I was saying that we already seen the drift components. Now we'll be looking a bit into the diffusion component to go further towards the recombination and generation models, because this also needs to have you also need to have a good understanding of. Okay, let me, sorry, is my screen visible? Okay, I guess not.
No.
Yeah, just give me a moment. I guess it is visible now, right? Is it visible?
Yes.
Yeah. So as the name suggests, diffusion. So I mean, we did cover what is diffusion in the PN junction. So what is diffusion is when the carrier concentration moves from high concentration, or the when the carriers move from a higher concentration to a lower concentration. So in a very simplistic term, if we have a lot of, let's say if a person is standing in a room and he sprays of some perfume, so what happens is the perfume particle gets scattered all over the room, and that is what is high concentration to lower concentration. The room does not have any particles of those perfume. So this is a very basic process of diffusion, that when the particles flow from a region of higher concentration towards a region of a low concentration. Okay, again. Yeah. So this is what diffusion is. Now what we'll do is we'll consider diffusion. First of all, we need to derive some of the formula. So what I'll consider is, so let's say this is the concentration of electrons in terms of x, that is the position. So let's say this is x equals to 0 at some, I'm talking about a semiconductor bar. Let's say this is x equals to 0, and let's say the semiconductor bar is L length long. So this will be, or let's say, yeah, L length long. So let's say this will be L by 2 and L by 2. So what we have is, let's say we have a straight concentration like that. So what I can say is, because of the finite temperature, electrons have random thermal motion that we have already established. The electrons at x equals to minus L, let's say here, let's say this is minus L or minus L by 2, and let's say this is x at L by 2. So the electrons at x equals to minus L, there will be one mean free path on the left side, and it has a equal chance of moving left or right. Similarly, the electrons at x equals to 0, what we have is it has a equal opportunity to move here or here. Similarly, here it has a equal opportunity to move here or here. So what we do is we try to calculate the average rate of flow of electrons. Let's say the flow of electron is given by F. So for the electron which is at x equals to 0 plane, let's say this, what we have is it has a probability, uh, let's say n equals to minus L times L by tau c. So the flow of electrons, so this is nothing but the speed, because distance upon time is speed. So it has a probability that the electron will come from this. So I have written this. So let me simplify this. I'm writing x equals to L and x equals to minus L. So there is a probability of electron coming to this point is half of n minus L times the total length by the collision constant. So if I try to simplify it, it will be again n at minus L tau c times L. So similarly, what we can write, the average rate of electron flow at x equals to plus L, if I now say. So what it will be? It will be nothing but half of n at plus L, the concentration, and L by tau c only. So the total flow will be again similar to that, n at L times L over tau c. So now the net rate will be the, so if I talk about 0, so there are some incoming, there are some outgoing. So the average rate will be the difference in between the rate of flow rate of the first minus second. So if you just do it, I mean the only difference in these formula is the concentration at minus L and the concentration at L. So this is what we come up with, and we know that, as I said, that L upon tau c is nothing but the velocity. So let's say if I'm talking about the thermal velocity as of now, so it will be nothing but VTH by 2 times this whole thing. And what we do is, so there was a topic in this particular lecture that is a Taylor series expansion. So we try to linearize everything, and Taylor series expansion is one way to do it. So what we have, let's say we have a function, let's say we have some function fx. So the Taylor series expansion of this function is given by f at 0 plus x times that of f derivative. So if I write across x equals to 0, so this is the function, then uh, so f dash x is nothing but d fx over dx, that is the differentiation, and plus so on. So the second term will be x square by 2 factorial. So this was 1 factorial, then f dash 0 and so on. So it goes on and on. So this is double dash, that is that means the double derivative. So now using the thermal, sorry, not the thermal, but the Taylor series expansion, we can linearize the n at minus L and n at L. So n at minus L will be, as I said, n at 0 minus L. So this is what is x now. So I'm doing the function of x. So L will be replaced by x over here. So this is x. So I've replaced. So it was plus x by 1. So since x is minus L, so I'm writing minus L dn over dx. Similarly, n at L will become n at 0, and there will be a change, that is the plus L dn over dx. Right. So if I try to put these two things here, what will happen is these two will cancel out because so these two will cancel out because there is a subtraction in between, and the net flow of electron will be Vth by 2. It will be minus L dn over dx, that is the first term, and again minus dl dn over dx, because n0 and n0 will cancel out, so it will come out to be minus L Vth and dn over dx. And yeah, so now we know that in general, so this is the, if this is the rate of flow, so charge multiplied by the rate of flow will be nothing but the current density, because flow of charge multiplied by, I mean this is the differential term, so if we multiply it by the actual charge, it will give me the current density. So if I try to write now J diffusion times for not times but for electrons, it will be nothing but minus q for the electron. And now if I try to replace everything, it will be ql Vth dn over dx. Now again, so the diffusion of electrons from a higher concentration to a region of low concentration. So what is happening? It is producing, I mean, it is producing a flux, and we know, we have established that mobility is nothing but q tau c by mn star. So we have already seen all of these things. We have seen the thermal velocity, it is nothing but kt by m star or mn star. Let's say if I'm talking only about electrons. So these are all the previous things that we have already established. So if I try to now substitute these into this, it will come out to be, I mean, let's try to solve it. So that J diffusion by N will come out to be Q tau C Vth square. So L I have written tau C into Vth, that was initially there. Then what I'm doing is now Q tau C, and okay. So what we have is Vth square. So Vth square will be this Kt by Mn star. So I'm writing that Kt by Mn star times dn over dx, and this we sorry, this I have just told you, this is nothing but q tau c, sorry, wrong circle. So q tau c by m star is nothing but the mobility, right? So J diffusion for n will come out to be mu n kt dn over dx. So yeah, so this kt is not in terms of electron volt, so let me write the q times q, so that this will be nothing but the Boltzmann constant, that is what we write as Vt. So if I just see this term, So I multiply divided by Q. So this term is also known as the diffusion constant, and it is denoted by dN, capital Dn. And the final J diffusion for n type comes out to be Q dN over dx, where dN, as I said, is nothing but mu n kt by q, or yeah, I just write mu n kt by q. So this is nothing but Vt. So you can also write Vt directly. So similarly, if you try to do it for holes, so there will be only difference in the plus q and minus q charge, and the final expression will come something like minus q dp dp over dx. I mean, this is straightforward. There is, I mean, just the sign will be opposite or something like that. So now what I can say is, so for holes, first of all, let's say the total current density was, one was the drift component and the second one was the diffusion component that we have just established. So this is nothing but pq mu p times e, and the jp is nothing but, so this is minus q dp dp over dx. Similarly, for electrons, the Jn will come out to be, so the first component will be nq mu n e, the second component will be q dn over dx, and the total component will be jp plus jn. And there is one more relation that comes out of it, is the Einstein relation. You might have heard of this Einstein relation. So what we have is, I have just said you that mu n vt, so this vt is nothing but kt by q, and similarly if I said that dp will be mu p kt, right? So from this what we can write is dn upon mu n is vt and dp upon mu p is vt. So this is what the Einstein relation is. This is what we call as the Einstein relation. And vt, I can rewrite so that it is not confusing. So it is kt by q, which is 26 milli electron volts. I mean, we have established this at T is equals to 300 Kelvin. You try to put the values also here by putting the value of K and Q. The exact, the formula for Vt come out to be T by 11,600 volts. Sorry, this is millivolt, not milli electron volts. Yeah, where here T is in Kelvin in this formula. So this is what we have for the Einstein relation, and this is the diffusion component. I mean the total components that we need to see first. So if we now have the idea for the components, so now let me move towards let me let's solve a very simple problem. I mean that will help you in clarifying better the things. So let's say what I do is, let's say I'm taking a semiconductor, let's say I'm taking a gallium arsenide, and I have this donor impurity given to me as some ND naught constant exponential of minus x by L, which is for the case when x is in between 0 to L. Here L value is also given, which is 0.1 centimeter. Here ND naught value is also given, which is 5 raised to power 5 into 10 raised to power 16 per centimeter cube. Mobility is given 600, not 600, 6000 it is given, centimeter square per volt second. Temperature is 300 Kelvin. So what we need to find is the induced electric field. By induced electric field, it means the built-in electric field that generates a drift current. Okay, that is a good question. That generates a drift current which compensates the diffusion current density. Okay, that generates a drift current density which compensates the diffusion current density. So do you understand what I'm trying to say here? Any idea what I mean, how do we start to solve this thing? We need to find the value of E such that the drift current density is compensated by the diffusion current density. What does it mean?
And we have to equate it.
Yeah, kind of like that. So as I told you that because since this is a n type of problem, so I mean this is a nd problem, so the total component is nothing but the drift plus the diffusion.
Vision.
So now what the question is saying that we need to generate our current density such that the diffusion current density compensates it. So we need to have a total current of zero, right? So this is,
Yes.
yeah, this is what we need to do. You have both these formulas and rest everything is given. You need to calculate the electric field. I mean, this is very easy if you try to do it. Just try to do it and let me know the steps you are doing and what is the answer that you are getting. You can take 5 minutes because this is a good problem. Any progress made? Okay, so let me also try to solve it side by side. So what do we have is J drift, that is NQ mu NE, plus J diffusion, that is Q dN, dN over dx. This, and this is nothing but zero. So we have n which is given as nd, which is a function of x. So let me write that ndx mu ne plus q dn ndx, which is a function of s, equals to 0. So now I'm just substituting the value. So this is nd naught exponential of minus x by l mu n e. So let's say I'm equating this, and this will be now minus q dn and the differentiation of ndx. So the differentiation of this term will be anyone?
Uh, ND naught, so that constant ND naught
Yeah.
divided by minus 1 by L
Uh,
into e to the power of minus.
Multiplied by 1 by l, right? So exponential
Yeah,
of ax is a exponential of ax.
yeah, it's 1 by.
Yeah. So and then
We have e to the power
exponential
of
of, yeah. So this is getting cancelled. This is getting cancelled.
Q you have missed on the other side.
Where?
Q,
Oh,
Q.
yeah, yeah. So q is also getting cancelled. So I've
E is equal.
raised mu n e is, okay, this negative sign is also going from this. Mu n e is dn over l. So the electric field that we need to calculate is coming out to be dn over mu n l. And we have everything, I guess, given in the question.
The Dn is kT by Q
Yeah,
into Un.
yeah. So dn is vt into mu n. Okay, so this is also getting answered. So it is nothing but vt over l, and the temperature is 300, so it is 26 millivolts divided by l. L is given, yeah, zero point 0.1 centimeter. So if I write it in volts, it will be 2.6 volt per centimeter. Minus 3 minus 1 minus 2, no, it's 0.26, I guess. 260 millivolt, yeah, 0.26 volt per centimeter. Make sense? Is there any doubt? This was a good problem, so if you have any doubts, please ask. Okay.
Yeah, it's correct. I got 26 volt per meter. Okay. If you take 10%, yeah, it's correct.
Yeah, I mean, in general, we always keep in centimeter because the doping is always given in centimeter in the problem. So yeah, you can convert that. That is no problem. So now, I mean, this was more of a some of the part that was missing before to have to go towards the drip diffusion models. So there is a good chunk of this generation and recombination of excess carriers. So as we have established that there is a lot of generation and recombination of electrons and holes. So recombination is nothing but the formation of electron holes pairs, right? When the electron hole meets, so they recombine and make a electron hole pair. So it can be done through various ways. So we have a lot of models that are present in, let's say, a simulation tool, which we call as TCAD. So you might have heard something like SRH recombination, Auger recombination, yeah, something like that. So these are different types of recombination and generation that happens inside TCAD. So first of all, if I talk in very general, so let's say I have put up some optical energy which have the energy h nu. So this, if this energy is greater than Eg, right? So what happens? I mean, and this is a basic photoelectric effect. So can someone tell if the applied energy that I have applied, that is h nu, is greater than that of Eg, what will happen? Let's say I've applied it on a metal plate. So what will happen now?
An electron will move out.
Yes, yes, exactly. So the these photons, whatever the optical energy I've applied, they will interact with the valence band electron, and since the energy is more than that of the band gap, So what will happen? The electron can elevate, the application of this energy will elevate the electron into the conduction band. So now what happens is this valence band contains many electrons, right? Those are not movable, but the conduction band is always empty. I mean, initially, if we are talking towards the equilibrium, so initially it is empty. So what happens is the probability of interaction is very high since h nu is greater than Eg. So if I try to write, or let's say this is a valence band, this is a conduction band. So it was full of, let's say these holes are electrons. I mean, sorry for the bad drawing. So what happens if I apply energy which is greater than that of Eg? So let's say this electron goes towards the conduction band. Now it is free, like it is a free moving electron, right? So it generates current. Now what we are left with, so the as I said in the initial lectures, that the occupancy, oh, sorry, the what to say, the vacancy created by this electron is nothing but the hole, right? There is no actual hole, but the vacancy created by the electron is hole. And we have a lot of other electrons in this valence band. So let's say I'm filling up the electrons now. So what happens is now this electron will interact with this hole and they will combine and make a electron hole pair. So this is what is recombination. So first of all, what happens is there is a generation of hole, right? So also this interaction of electron hole pairs generates a electron hole pair. So this is what we call as generation of electron hole pair. I mean, I'm first trying to tell you the basic terms, and it only happens when this h nu is greater than that of Eg. This is also called as hc by lambda. And so it, what we need, let's say we try to calculate the wavelength, so it will be something less than hc by Eg. And if we try to solve it, I mean hc are all both the constants, so it comes out to be something 1.24 by Eg in electron volts, and this whole is in micrometer. So we need to have a wavelength lesser than whatever this value to have the electron, uh, to have the generation of electron hole pair. So let me try to, so let's say we have a UV light which is getting over this metal plate, and the frequency for this UV light, let's say, or the wavelength is given out to be, let's say 700 micrometer. Oh, this is too much. It should be in nanometers. Yeah, something like that. So uh, you need to find the minimum Eg possible to generate the electron hole pair. I mean, this is quite straightforward, but yeah, just to give you idea, let me know what is the answer quickly.
1.7285 electron volt.
Yeah, so it will be something like 1.24 by zero point 0.7 in micrometer. So this will be 1.7.
72
Yeah.
electron volt.
So this should be the band gap to have the generation of electron hole pairs. Now similarly, as we have the generation, so what happens is, now if I, let's say if I dope this, whatever this equilibrium conductor was, or sorry, semiconductor was, let's say in equilibrium we have this Np is equals to Ni square, right? So once I dope it, or let's say if I inject some more carriers into it, So what will happen? This NP will become greater than N square, right? Because we have more doping. So either N will increase or P will increase, and this does not hold because we are not in equilibrium now. So since we have this unequilibrium state, so what happens is whenever this equilibrium state is disturbed, so if we are not applying anything further, so there exists a process in which what happens is they try to restore the equilibrium. So in this case of injection of excess carrier, as I said that I have injected, let's say carrier injection I have done, due to which equilibrium is disturbed, right? So to restore equilibrium, what happens is the mechanism that restores this equilibrium is known as the recombination. And recombination of the injected minority carriers with the majority carriers. So you need to run this that the minority carriers uh, recombines with the majority carriers. We'll see an example. What does it mean? I mean, this is straightforward. So I mean to say it in single line. So generation is a process where electrons and hole are created because we are creating, and recombination is a process where electrons and holes are annihilated. That is, we are uh, recombining them. So there is no generation of those electron hole pairs. So now there can be different types of recombination and generation. So let me name few and try to explain it in very simple language. So the first one could be, I mean, this is the straightforward one, band to band generation and recombination. So in this, as the name suggests, what happens is, okay, so just for the ease, I'm making the electron with this cubes and the holes with circles. So this is the valence band. It is filled with a lot of, as we know, a lot of electrons. And if we apply energy uh, which is greater than that of this band gap, what happens is these move out and they are here now. So I mean, there were two electrons there, they moved out, and there are holes here, right? So this is nothing but band to band generation. I mean, as the name suggests, this is very simplistic. Makes sense? Similarly,
Yes.
if these electrons move back to the conduction band now, so what will happen? If these moves back, so there will be, I mean, there were holes before. Let me make the before picture. So if we can somehow move this electron back, that will be nothing but B2B recombination. So I mean, I have given a very basic example. So I have considered a direct band gap semiconductor, which is in thermal equilibrium. And now, when how does it happen that these electrons are moving from valence to conduction? We need to apply some energy. So what happens is in every as the temperature increases, what we have seen is there is a lot of scattering, right? There can be lattice scattering, there can be lattice vibrations, or the atoms are vibrating due to the excess temperature, and they cause some breaking of these bonds, and this is how these electrons or electron hole pairs are generated. And in terms of band diagram, as we have seen, the thermal energy enables the valence electron to make an upward transition towards the conduction band, which is what is creating this band to band carrier generation. And similarly, when electron makes transition from the conduction band to valence band downward, that is what is creating a electron hole pair, right? So they are getting generated. So that is what called the reverse process or the band to band recombination. This was the easiest one. Then there are few more. Let me tell you the most important one. Uh, Let me skip all of this and just tell you the most important one, which is auger recombination. This is the most used model in TCAD also. So this generation and recombination as I said, this was something called band to band. So this is called as through impact ionization. So does anyone know what is impact ionization? Any basic idea?
Yes, I mean, like when we apply the greater voltage because of the high electric field, the electron starts moving at the like they accelerate, and then they impact the gate also.
Yeah, they accelerate. Yeah, till then it is right. So what happens after the acceleration? They will collide, right?
They collide, yeah,
Yeah,
and I know till there.
yeah, yeah. I mean that is
It
fine in that.
also affects the gate oxide. I
Yeah, yeah. So you are
am aware.
talking about a MOSFET right now. We are just talking about a material. So that is fine.
Okay.
I mean, no problem.
Mhm.
The basic idea is this only, that whenever we apply a very high voltage, the electric field is so high that the electron gains some energy and they start to collide. So what happens is once the electron collide with some other electron, so let's say this is the electron, it collide with this electron. So it loses the energy and it gains the energy. So this process goes on and it also collides with some other electron, and yeah, this goes on and on. So this is what we call as impact ionization. So as the electron which loses energy, it recombines with a hole in valence band. Such, so I mean, let me try to make a picture that will be easier to you. So let's say this electron is, let's say this is EC, this is EV, since we are not in equilibrium. So what happens is these electrons are moving with a very high velocity. So what happens? These due to this high velocity or the application of let's say very high voltage, we have this impact ionization, and impact creates this electron hole pair. So this is what is, I mean, mainly recombination. But if I now try to explain, let's say these two are the electrons in the conduction band, and now this, what, as I said, that this electron, let's say, collides with this, so this will lose energy and it will go back to this valence band. So this is what is the recombination, right? So this recombination is what we call as Auger recombination. I mean, this is a better figure to explain. So let's say due to a very high energy, electron collides with the other electron. So this one will lose energy and this one will gain energy. So once it loses energy, it comes back to this valence band and the recombination happens, and this is what we call as the Auger recombination. Make sense?
Yes.
Yeah. So I mean, these are the two most important recombination and generation. And I mean, in terms of the equations, let me do that. I'll not I'll not go much deep into this because that will be very hectic. I'll keep the basics only for this class, and the next class, which will be, I guess, I don't know when it will be. I guess it will be on the 21 now. So in that, I'll do all the steps for the derivations for the continuity and all. So let's talk about the recombination and generation rate now. So what happens is, I mean, let's say this is some material which is some, so there will be, after application, there will be a certain recombination generation, which I'm denoting as RG. So for electrons, the change of concentration with respect to time, it could be due to, it could be due to current, the formation of current. It could be due to the recombination generation. So it can happen anywhere. I mean, once these carriers collide with each other, so they can recombine, generate, and it is one of the factor, and they are all time dependent. Or it can be due to, let's say, any other process. The two main components are because of current and the recombination generation. Similarly, for holes, it will be some same, but it will be dp by dt. It will be dp by dt due to current plus dp by dt due to recombination generation or any other process, right? So now what we know is at thermal equilibrium there is no temperature bias. So the total dn over dt is will be always zero. If I say, let me write it, otherwise it will be confusion. So at equilibrium, this will always be 0. Each of the component will be 0 even. So there will be no formation of current because we are at equilibrium. There will be no recombination generation, and it goes on and on. Similarly, it will be for the whole, so I'm not rewriting it. But now let's suppose we move out of this equilibrium and let's say current is introduced in this material or light is incident, something like that happened. So now we are not in equilibrium, right? So, but one thing to add is, let's say we move out of equilibrium, that is fine. But we are in a steady state. Can anyone tell what is a steady state? Any idea? Steady state, as the name says, I mean, it is the answer is in the name only.
I mean, the rate of generation would be, I mean, constant.
Yeah. So steady state means that everything has happened. I mean, there could be a case that there will be a current, but it is not zero. There will be a recombination generation which will not be zero. But in the steady state, what has happened is the final total state is still zero. So this is what steady state implies, that whatever has happened has already happened. Now the material is in a steady state. So the total component will always be zero for this. So this is one more thing. So at steady state, the rate of change of concentration with respect to time remains zero. And like we have finite values for all the other cases. And now if we just neglect, let's say remaining other processes, that is what I was writing, any other process. So let's say we neglect it. So what we have is, let's say we focus only upon the recombination generation. That is what we are talking about. So the dn by dt total will be nothing but, if I only focus on this, it will be dn by dt due to rg, right? And it will be nothing but the generation rate minus the recombination rate. Whatever the generation is happening, it is getting compensated by the recombination. So this Gn is the generation rate, and it will be number of electrons per centimeter cube per second, because this is the rate. Similarly, this is a recombination rate, and it will be recombining with the same unit only. Sorry, so it will be per directly, so it will be per centimeter cube per second, similarly like this. Yeah. So one thing that happens is, as I told you, that at steady state already everything has happened. So at steady state, dn over dt total has become 0, right? Which will make gn is equals to rn. Make sense? Any doubt in this?
Yeah, got it.
Similarly, gp will be equals to rp for the n type of case. So at a steady state, the generation rate of the excess carriers is equals to the recombination rate of excess carrier. So that is I want to emphasize only. So that means that n is, let's say n naught is the actual carriers and delta n is the excess carriers. P is P naught is the actual and delta P is the excess carriers. So this is at thermal equilibrium. What I am writing with the naught is at thermal equilibrium, plus some excess electron pairs will be generated. P is P naught plus some excess hole concentration will be there, right? Now there are 2-3 cases to discuss here. I mean, there are also some some assumption made. So what we use the term is for low level injection. So we are injecting a very low carriers. The amount of carriers is very low. So what happens means is the delta n or delta p is very very less than the equilibrium states, right? Similarly, the delta n or delta p will be very very less than the equilibrium p naught state. So this is in n type, this is in p type. So I mean, just try to focus on few terms. First one was the, I mean, here was a low level injection. Here it was steady state. I guess yeah. And there are few such as equilibrium, non-equilibrium, but I am trying to emphasize on these 2-3 terms currently. Yeah. So where was I? Hmm. So for low level injection, this delta n or delta p will be very very less than n naught. So basically n will become n naught. That is what I'm trying to say for low level. So now recombination rate. right? Recombination will be given by, recombination is happening of, as I said in the initial time, that the minority carriers are recombining with the majority carriers. So minority carriers, let's say for p type, will be delta n times the collision time. So this will be for p type, and delta p by tau p for n type. Let me repeat again, the recombination is always of minority carriers with the majority. So in p type, the minority carriers will be delta n, right? Make sense still here? Any doubt or confusion?
Can you just explain one more time?
Oh, let me take an example if it is getting confusing. So let's say n naught is, sorry, not 15, but what I'm trying to say is, let's say n naught is 10 raised to power 15, p naught is also, let's say, 10 raised to power 5. So this is which type of semiconductor?
N.
Yeah.
Hmm.
So now what I'm trying to say is delta n is equals to delta p. These are the minority carriers, right? So that will be 10 raised to power 5 per centimeter cube, no? So n is n naught plus delta n. So n naught is 10 raised to power 15. Even if you have this delta n, it will be 10 raised to power 15, no?
Yes.
And p will be p naught plus delta p. So that will be twice of 2 raised to power, twice of 10 raised to power 5. So
Uh-huh.
so what I'm saying is, when we inject some holes in a n-type semiconductor, then the time taken by these holes to annihilate is nothing but this. This is the recombination time. So since I've taken a n-type of semiconductor here, so it will be, the recombination is happening for the minority carriers. So that is why it is delta p by the lifetime of that tau p. So the recombination is happening of these minority carriers, not these. There is no recombination happening here. Still
Okay.
confused.
Yeah, got it. And,
Okay. Yes,
okay.
yes. Yeah, yeah. Tell me.
The recombination is happening for the minority charge carriers. If it is N type, it's P.
Uh, See, I mean, if you remember this diagram,
Mm-hmm.
so once these, what is this? Holes is getting created and electrons is here. So recombination is happening. The minority carriers here are holes. So the recombination due to the loss of energy is happening because due to in the hole only. That is what I'm trying to emphasize.
Okay, yeah, yeah.
Yeah. Let's see one more thing that has been left out, or in fact not left out but not properly done, is the quasi Fermi level, because we are talking about equilibrium, non-equilibrium, so that will come into the picture. So let me refresh your minds. So let's say I'm taking an n-type semiconductor which is having nd this, and I, let's say, 10 is per 10 per centimeter cube. So can you tell what is ef minus ei if it is in equilibrium? Very straightforward, right?
KT by Q
Yes.
ln of NT divided by Ni.
Yeah, it will be this only,
Mm.
and it will be 0.026 ln of 10 is per 5. I guess it will come out something around zero point 0.3 electron volts. So this is quite easy. I mean, in equilibrium, we know that this is the formula and all. But now in the same semiconductor, let's say what I've done is I've injected 10 is per 12 electron hole pairs. Sorry, not injected, but there are 10 is per 12 electron hole pairs that are generated. So what will be EF minus EI now? This is the question. If you have understood the minority and majority correctly, you will be able to answer this. So let me do it by myself. That will make it easier. So what we have done is we have created 10 is per 12 electron hole pairs, right? So that will be the excess carriers. which is this only. So now if I try to write n, which will be n naught plus delta n, it will remain 15 plus 12. I mean around 10 to 15 will remain, right? And p will be p naught plus delta n, which will be twice of, sorry, the initial p naught was what? Yeah, we can calculate p naught by np is equals to ni square.
Yeah.
So p naught will come out to be 10 to the power 5. I mean, yeah. So it is 10 to the power 5 plus 10 to the power 12. That will be 10 to the power 12 only. So now what we have is, we have, you just calculated it by this formula, exponential of EF minus EI over KT, and n will remain same, Ni will remain same. So EF minus EI will remain same, that is, what did I say, 0.3 electron volt, I guess. But now we have a p-type thing also. So for p-type, if you remember, we have this exponential of EI minus EF over KT. So if you try to calculate EI minus EF over KT now, due to this excess carriers, what has happened is there is one more Fermi level that will be 0.026 ln P by Ni, and P is 10 to the power 12, so it will be 10 to the power 2. And the value of this will come out to be, you calculate quickly, this is coming out to be point,
119.
yeah, 0.12 electron volt.
Yeah.
So what it is exactly saying is, we have a conduction band, we have a EC, we have a valence band, we have a EV, we have EI in between. So there are now two Fermi levels. One is this EF minus EI, which is 0.3 volts or electron volts, and one is EI minus EF, which is EF, and this is 0.12 electron volts. So these two Fermi levels are known as quasi Fermi. So we need two different Fermi levels to define due to the non-equilibrium condition, right? So this is what is quasi Fermi. Quasi means, I mean, more than one. So from the above example, what we can say that equation, these and this, I mean, this equation and this equation is, uh, we need to consider the different Fermi levels for these equation, and these different Fermi levels are known as quasi Fermi. So since we are having some different Fermi levels, so in general what we write is, for n type we write EFN, and for p type we write EFP. So these equations are generally replaced by this only, and this p is given out by Ni exponential of EI minus EFP over KT. So these are the quasi Fermi level. Make sense?
Yes.
Okay. So now
This
since,
condition occurs only when we inject non-equilibrium condition, and when we inject the uh,
yeah, so by injecting the carriers, we are having a non-equilibrium. So it can also happen if we apply a voltage. You might have seen the band diagrams of PN junction at applied voltage. There were two different Fermi levels. Remember?
yeah, I got it.
Yeah.
This.
So whenever the device is not at equilibrium, there will be multiple Fermi levels. That is what is quasi Fermi level is. So okay. So there is a very big derivation to come up, which is the continuity equation derivation. I mean, so before going into this, let me see if we can cover all of this in a single lecture. Mm. Okay, so let's see some question first. If the time permits, then I'll start. I mean, is there any doubt in the things that I've explained till now? The quasi Fermi, the low level injection, the steady state, and the recombination generation. And initially I explained, what was that? The diffusion and the drift part. Any doubts in these things?
No, no, we can
Yeah,
go.
so that is fine. So now let's see some problems. I mean, there are very basic problems in this lecture, so that is why I do not like indulge in many problems because it is more of a conceptual topic. So the first problem is which of the following statement is not an assumption made in drift diffusion model? So not a drift diffusion model. So this is, I need to make you explain the drift diffusion model, but we have already seen there are three, four conditions. One is low level injection, one is steady state. So there are few more. The next is the complete ionization of dopants. So in the previous class, we were calculating like some of the dopants if they are not ionized. So what is the rate and what is the energy level, all that. So in DD model, what we always assume is there is always complete ionization of the dopants, and it is non-degenerate, always non-degenerate. So what is non-degenerate? Can someone tell?
I mean the band gap, I mean not the band gap,
The Fermi level.
the Fermi level and the conduction band. It is more than kT, more than zero point
Uh,
0.3 electron volt.
okay. I mean, in very simple words, we have degenerate, non-degenerate. So
Yeah,
all the
in,
things that we have done is always non-degenerate, in which the Fermi level always lies below the conduction band or valence band, lies above the valence band.
mhm.
For a p
And
type,
the difference is very near to the intrinsic Fermi level. I mean, not near to the conduction band. Yeah.
sorry, what are you saying?
I mean, the EC minus EF will be
Okay.
there's a term 3 kT.
Yeah. So it is always greater than 3 kT. So the 3 kT is
Yeah.
around 0.808, something like that. So 0.026 multiplied by 3 only.
Mhm.
So I mean
Yeah.
that is not much. It is not like that it is close to EI, but it is not close to EC. That is what
Yeah.
we can say. And
Mhm.
for degenerate, the Fermi level is either inside the conduction band or inside the valence band.
Mhm.
I hope you can assume. I mean, you
We
can.
don't study degenerate, right?
Yeah. I mean,
In
in
this
general, we see non-degenerate only. So this can happen when the doping is very, very high.
doping is very, very high. Okay.
So you understand that, let's say N type semiconductor, so EC will go on, sorry, EF will go on towards EC if we increase more and more doping. Basically, this formula only, N is Ni, not EC, sorry. N is Nc exponential of minus EC minus EF over KT. If you remember this,
Mhm.
so if we make this N greater than that of Nc, so EC minus EF will become negative. That is, the Fermi level will go inside. In general, this Nc is 10 to the power 19 per centimeter cube if you remember for silicon. So let's say if we dope it around 10 to the power 20 per centimeter cube, this will become degenerate.
Okay.
Yeah. So all the things that we study is for non-degenerate. The silicon doped is always non-degenerate case. So these are the few things that we the assumption are made, and the assumption that is not made is temperature gradient is considered. There is no temperature gradient that is considered. The temperature remains same throughout the device. So for this, the correct answer will be B. We'll see the all the cases for these three. I mean the derivation type of thing, that what are the drift diffusion equations for all of these different cases that we assume, that we will see later. But yeah, let's see some problems first. So it says consider a semiconductor. Okay, let's leave it. So this is a concept called d by length. So this is also come under a derivation. Okay. So this is now a generic question. Which type of semiconductor is preferred for high speed application assuming same type of doping? Any idea or any guesses? This is very easy, I mean.
Oh, yeah, N type. Okay.
Yeah, N
The
type, right?
mobility is more.
Why? Because it has higher mobility.
Yeah.
So high speed is always N type. Okay. Okay, so there's one more problem which says what characterizes Newman boundary condition. So let me give you a very basic idea. So there are two types of main boundary conditions. The first one is Dirichlet. The second one is Newman. I mean, these two are the only main ones that we study. In Dirichlet, what we do is, so let's say this is a semiconductor, this is the boundary. Let's say this is x equals to 0, this is x equals to L. Similarly, this is x equals to 0 L. So in Dirichlet, what we do is we specify the potential or whatever we want to specify at the boundaries. Like we give some finite value. Let's say this is A and this is L. For the Newman, what we do is we give the differentiation of that. So dV by dx at x equals to 0 is some value A, and dV by dx for x equals to L is some value B. This is the only difference in specifying the boundary condition, because any numerical will be solved using the boundary condition. If I hope you remember the Schrodinger equation when we are trying to solve for the infinite well. So what we are considering that at v equals to 0 the psi is 0, at v equals to L the psi is L 0, right? You remember this?
So the probability of finding the
Yes.
electron at the edges is
Yeah,
zero.
yeah.
Right.
So from there
Yeah,
we
standing wave.
from yes, yes. So from there we found out that this is the wave function that we have. So in any material we need to know the boundary conditions first, that what is the extreme conditions. So it can be done using two methods. One is a Dirichlet boundary condition, and the second is a Newman. So in Newman, the derivative of the function that we want to calculate is given as a certain value, and in Dirichlet, the value is given as a certain value. So this was the case for this, and Newman is the derivative. So is there any option like that? Specifying function values or the boundary. So this is Dirichlet, specifying the derivative. Yeah. So option B will be the correct answer. So both of them we never give because that is the extra step. And this is, I don't know what is this, but yeah, option B is the correct answer. Is there any doubt in this?
No, I mean, good. Understood.
Okay. So let's try to do this. Find the whole diffusion constant. So this is nothing but dn. Oh, sorry, dp. This is what we did in initially the derivation. The Einstein relation will help you solve this. Doped with trivalent blah blah and conductivity is this. I mean, this is very easy. Let me know what is the answer. Why is it taking so much time?
Option A.
Okay. So dp was mu p times vt, right?
Yeah.
Yeah, so mu p we need to calculate and conductivity is given, I guess. So conductivity is P
Conductivity is
mu
QP.
P.
Yeah.
Yeah, so mu P we can find out. Conductivity is given 1.28. P is given 10 to the power 16. U
One.
is 1.6 10 to the power minus 19. So this is 10 for 3.
800.
Okay, so this is 800. I'm not sure, huh?
No, it is 800.
Okay. So dB is nothing but 800 times of 0.026, which is 2.6 times 8, 8 6 is 48, 220.8 centimeter square per second. So option A is the correct answer. Okay, let's move ahead. Sorry for all this. I don't know what it is. So it says a P time. Let me see if we can do it. Otherwise, I can skip. It's a drive in a nice direction. I guess we can do it. Yeah, this is very easy. So give it a try and let me know the answer. Take 2 3 minutes and let me know the answer. This is very easy. The main thing is it is only asking you to calculate drift current density. And everything is already given.
Eight.
Okay, so let me solve. I don't know. So this is a p-type silicon sample. So the drift component will be E Q mu P E. Everything is already given. The length, width, doping concentration is given. Q we know. Mobility is given. Everything is given. This is too easy. Q is 1.6 times 10 for minus 19. Mu P is 500. Electric field is 1 volt per centimeter. So this is the answer minus 2. 1.6 times 5 is the answer. So that is 8. Yeah, this was very easy. Let's move ahead. Okay, suppose we have a function fx is sin x and we want to approximate value at, yeah. So does anyone know the Taylor series approximation of sin x?
No, I don't remember. There are two series McLaren and
Yeah. So this is x minus x cube by factorial 3 plus x5 by factorial 5 and then
minus
minus x7 by factorial 7. plus, and it goes on. So I've made this easier, I guess, for the problem. So we need to find the Taylor series approximation of 0.1. So let me know the answer in maybe 2 minutes. This is easy. Mm.
0.099833.
Sorry, 0 point
99833, the option B.
this.
Yeah,
Okay,
like
so we
we
need
just
to do the point 1. So it will be point 1 minus point 1 cube by 6 plus point 1 is for 5 by,
120.
so I mean this is 10 is for minus 1, so it is minus 5. This is 10 for minus 3. This is 120.
Yeah, yeah,
I guess
120.
you don't need to calculate further.
Mm-hmm.
This is something point 1 minus, so I mean all the options are greater than that, so this should be the answer.
Yeah.
Okay, let's do one more problem. So let's say we have a p-type semiconductor having the doping density Na. Okay, so now what I did is uh, the concentration of the same p-type semiconductor is increased 10 times. Find the change that has happened in the Fermi level. Uh, do you, uh, do you understand the question?
The concentration of the same. Yeah, and the P dopant is increased to
Yes,
10 times.
yes, yes, yes. So it was
So,
Na, it is increased to 10 Na basically.
so we have to find the change in the EF.
Yes, whatever the changes that has happened in the EF, you need to find. Take 2-3 minutes and let me know.
The answer I got is minus 0.059
0.059.
electron volt.
So let me also do it. This was very easy. I mean, so
KT into ln of 10 power minus 1.
yeah, that will come. I mean, so we have Na, we have 10 Na now. So let's say EC, EV. So since this is a P type, so let's say EF was here and we have increased it to 10 times, so it will move closer to EV, right? So this is, let's say EF. Okay, sorry, need to make it again. So this is EF and this is now EF dash. So this difference we need to calculate. So yeah, EF dash minus EF will be something negative. So for the first case, how we can do that? We can do it either by EI minus EF or EF minus EV formulas. So that is the main, I mean, two methods we can approach. So let me do it by the NV formula because we have not used it much. So P is NV exponential of minus EF minus EV over KT. So for the initial case, what we have is P is NA exponential of minus EF minus EV over KT. And if you try to calculate EF minus EV from here, it will come out to be VT ln NA over NV. NA over NV or EF minus.
NV over L.
Yes, yes.
Yeah. Yeah, yeah.
NV will be higher. Yes, NV over NA. Now what we have done is we have changed the NA to 10 NA. So now with this the Fermi level will change to, let's say, EF dash is what I have written. So EF dash minus EV will be VT ln NV over 10 NA.
And then, yeah.
So this is what we need to calculate. So if I'll subtract these two, it will be EF minus EF dash will be VT ln. So if we divide these minus, so it will be 10 minus means divide, so 10 will come over. Yeah,
No,
yeah,
should we take EF dash minus EF,
yeah. I
right?
mean whatever we do, but if I subtract this from this, so EF minus EF dash will be VT minus.
Like what I have done is EF dash minus EF. So I got VT ln 10 power minus 1.
Yeah, yeah, that is fine. I mean, so EF dash, sorry, EF dash minus EF will come as VT ln 1 by 10, that is 0.1 or 10 minus 1. So
Uh-huh.
this is the answer. I mean 0.026 times ln 10 minus. So this is 0.026 times 2.303. So 2.306 twice.
0.05986.
Is it are you sure na 59?
Yeah, yeah, yeah.
So
Using
this will be
calculator.
minus only.
Yeah, yeah. 86.
Yeah. So this will be the answer. That is correct.
Yeah, okay.
So yeah, I mean these are some of the basics. I didn't want to like cover the long derivations because I want a single like 1.5 hour run for that. So maybe we can stop today's class because I have explained a lot of concepts. So I'll let you all grab these because if you grab these, so next class will become very simple. Uh, so if I have come to the, so there are a lot of generation and recombination models that we'll be seeing in the next class. So there are 3 4 cases that I have already been telling you from the initial part, and I have tried to explain what these cases means. So we'll see the derivation for each of these cases. That is the rate of recombination generation. How will we do that? Yeah, these 4 cases we'll see. I mean, this will always be the assumption, and these 3 we can play with. So yeah, we'll see that in the next class. So for today's class, if you have any doubts in any section, you can let me know. Otherwise, we can stop.
No doubts from my end.
Okay. So now we'll next meet on 21, I guess, if I'm not wrong.
We will now. Yeah,
Yeah.
20.
Yeah. So please do watch all these recordings and then
Yeah.
come to the 21st class because that will be very easy then.
Yeah. No, thank you, Anant.
Yeah, yeah, no problem.
Thanks a lot.
Thank you for joining. Bye bye.